Today we have the great pleasure to welcome Professor William Parnell, who is the head of the Mathematics of Waves and Metamaterials group at Manchester University. So Professor Parnell is an expert on the theory of cloaking, elastic metamaterials, and today he will talk about silence is bliss in a Platonic relationship. Professor Parnell.
Okay, thanks all. Thanks, Seb, and hopefully everybody can see the talk full screen now. So firstly, thanks to Bogdan Wemmer and Sebastian for organising this series. It's been a fantastic series of talks. I've seen lots of them, not many live, but I've seen lots of them on YouTube afterwards. So, you know, it's a fantastic repository of talks and something good that's come out of the pandemic and has allowed people to communicate and, you know, connect in a way that obviously we couldn't do before. So thanks to them for keeping it going as well. Doing that for a year or over a year actually is no mean feat, I think. So thanks on behalf of the whole community for that. So today the talk's kind of split into two. The bulk of it is on this work here, and then there'll be a little bit at the end if we have time. I tried not to make the talk too long, but of course things always drift. I'll try to keep it focused. So the title, credit goes to Tom and Chuck Him, Silence is Bliss in a Platonic Relationship. And really it stems from some work that we started many years ago. So we were sort of inspired originally by the work of Guevara-Vasquez and Graham Milton on active cloaking. And so we followed some of that work up with Andrew Norris. We derived some explicit relationships for the source amplitudes, as I'll go through in a moment. And one of the things that I really wanted to do was to do things in 3 dimensions. It's always the real world. So really that work was always something I wanted to do. And when Chuck Him came along, he's a very talented student. So he was seemed to be the perfect student who could take that problem on. And he's done a great job with it, as I'll hope you'll agree looking at the work today. So just a quick discussion first about our group in Manchester, just in case you don't know much about it. We're a fairly large group for a mathematics department, so we've got 5 faculty. So Raphael Assia, many of you will know, who works in waves, canonical wave scattering problems. Anastasia Kissel, Tom Shearer in materials. Anastasia works also on kind of complex variable theory, waves, and the Wien-Hopf technique. Gareth Wynne-Jones, who works on kind of flexual on buckling and other kinds of materials problems. And David Abrahams, many of you will know, who was at Manchester, and now he's the head of the Isaac Newton Institute at the University of Cambridge. So pop over to this, to the webpage if you can. We've got lots of stuff on there, lots of videos about the sort of research that we do. And we've got a thriving group of postdocs and students who do lots of interesting stuff. So this is the kind of stuff that we do. So metamaterials is kind of only one part. It's a pretty important part, obviously, but we do work ranging from very practical experimental work on soft tissues and nonlinear elasticity and viscoelasticity. We sit at the sort of interface between experimental work and theory, and in particular we do a lot on kind of foams and nonlinear composite materials, syntactic foams in particular over the last few years, and novel materials design. And my background mainly, since my PhD, is in homogenization and micromechanics, and I sort of moved into multiple scattering, and of course that kind of naturally pushed me into the metamaterials direction. And so many people in our group look at sort of fairly mathematical formulations of canonical scattering problems. So that's the sort of thing we do. We've been fortunate to get significant funding over the last few years from a range of sources, and that allows us to do work both at the kind of theoretical end, but also on the industrial math side, which is always fun to me to kind of sit at that interface. So what we'll talk about today is active cloaking, so what's known as active exterior cloaking that many of you may have read about. We're going to do that in 3 dimensions, which is a bit of a challenge, but it's good to sort of talk through that. And it transpires that the distribution of those sources is actually extremely important. So if you want to, you can take the distribution of those sources to be anywhere, of course, active sources in 3-dimensional space, but it turns out that choosing a Platonic relationship, i.e. they sit on the vertices of the Platonic solids, it turns out to be an extremely efficient way of doing things. We'll talk through that method, and then provided we've got time, I'll sort of skip through a little bit of work that we've just touched upon recently which has looked at how you can exploit the giant monopole resonance in elasticity for kind of soft solids in order to sort of generate a low frequency resonance associated with what we think of as elastodynamic metaclusters. So that's the term coined recently in the metamaterials literature. So this is the kind of problem that we're interested in. We've got a sphere or any other object you could think about in an incident wave. It doesn't have to be planar, it could be any sort of forcing. And we've got L active sources. So the active source field here is UD, and so scattered field that you're trying to eliminate is US. Okay, so here's the notation. So UI is the incident field as you'd expect, UD is the active field, like I've said, and US is the scattered field, and we're trying to ensure that US is 0. K is the wave vector of the incident field when it's a plane wave, and we've got L active sources, and XL we'll think of as the position of the Lth active source. Okay, so capital L active sources. So we're going to use this terminology and notation as well. So U of X, capital U, is the notation for incoming waves, and V of X is for outgoing waves. So the kind of modal decomposition that we use, in terms of the standard kind of fundamental basis, uses that terminology. So you can think of the fundamental modes of scattering in terms of these pairs. So UN and VN is the incoming and outgoing vessel functions. And what we do, as is sort of classical, and look back to this paper of Fernando Guevara-Vasquez in this great journal Wave Motion, and the active field is therefore decomposed in terms of this outgoing sum over all of the sources, and these are the source amplitudes, of course. So what you might think of as sort of active sound control, typically would just use monopoles. So you might just have V0 here. Okay, but if you want to extend that into other regimes and multipole, then you sum this from n is, well, obviously you truncate it, but formally mathematically you go from -infinity to infinity. And what Guevara-Vasquez and colleagues did in their paper in 2011 is they found this nice integral expression for the active source amplitudes. So these are determined in terms of the incident field, which is of course assumed known, or you can measure it via some mechanism as it's incident on your object. Okay, the critical thing that I liked about this work actually is that the active cloaking methodology is independent of the scattered field. Okay, so it doesn't matter if you have an elephant or a sphere or a cat or a bird here, then you have the same active field. So the active field is not at all dependent on the scattered field, and it works in a way that essentially just completely nullifies the region interior to the active sources, whilst contributing sort of coherently exterior in order to be 0 in the region outside the active sources. And so this often comes up, if you submit a paper on this topic, then this often comes up via referees, because referees often say, well, what happens if you put something in here? Well, of course, in principle, nothing happens because it's 0. Okay, the field is 0 there, so it doesn't matter if you have something there, it is 0. Of course, in practice, when you start to truncate this modal sum, then it does matter what's in there, because some of that energy is going to get into the interior field, and then you will get diffractive effects and other things going on. Okay, so in reality, it does actually matter. And so the work of Guevara-Vasquez was very instrumental in what we did then subsequently, and what we did subsequently was to determine the sort of explicit forms of these integrals here. So you can actually work out what those integrals are for any form of expansion of the incident wave field in terms of the vessel functions, as you would normally do. So not much was done in 3 dimensions on this topic until 2013. So if you look in the nice acoustic metamaterials book, then there's a really nice chapter where Guevara-Vasquez and colleagues follow up on their initial work, where they implement the methodology into 3 dimensions. Okay, so they go through and they derive exactly the same kinds of expressions as you would expect in terms of the sort of fundamental bases in 3 dimensions, so the kind of classical spherical Bessel functions, Legendre polynomials, etc., etc. And then they implement that methodology in the specific case where you have 4 active sources. Okay, and you can see that in this specific case, you get very nice results. You get sort of active cloaking that you would expect. Okay. So what we wanted to do is sort of take that further and think about how you could actually extend that. You know, what's the kind of distribution of sources that you could use to take that further to make the cloaking better, or could you use a smaller number of multipoles? So thinking practically, if you would want to have practical cloaking, then you might want to have only monopole and dipole sources at most. So, you know, can you get away with that? How many sources do you need to do that? That sort of thing. And can we formulate that mathematically? So the key thing here is that the discretization of those surfaces, so these kind of delta C that make up your kind of cloaking region over which your amplitudes are integrated in order to determine them, it's quite expensive to do that computationally. And of course, when the number of sources becomes large, that becomes even more expensive. So firstly, is there an efficient way to do that? And secondly, it's quite difficult to sort of just visualize the silent region in 3 dimensions. So can we go beyond the L=4 case to do that in an efficient way? So first goal is to seek an efficient way to evaluate source amplitudes for a given incident field. And secondly, extend the method to source distributions that are located at the vertices of the Platonic solids. Why do we do that? Well, the nice thing, of course, about the Platonic solids is that you have these regular surfaces that sit between the vertices. And what that means is that you actually have the same kind of region to integrate over. So when you have here you have obviously 4 surfaces over which you can integrate, and all those surfaces are the same, and that actually helps you in terms of the implementation, as we'll see shortly. So let's just go back to the derivation of the source amplitudes, just to give you an idea of how this is done, because I realize that many of you will not have seen some of this work in the past. So we start off with the Kirchhoff-Helmholtz integral equation, and you have this classical result. So if we ignore the fact that there's active sources here for present, and we just think about some closed contour, you can think in 2 dimensions if you want to in this context, and have a closed contour delta C. And if you sit x inside delta C, then of course you have this relationship from Kirchhoff-Helmholtz, whereas if x is outside, then you have 0 on the right hand side. Okay, so y sits on this closed contour delta C. And so what you want to do is you want to choose some active field, UD, such that UI plus UD is 0, identically inside this silent region. But you want to choose UD so that it's 0 outside the active region, because obviously you only want the incident field outside that region. And so the kind of obvious thing to do really is to say, well, inside then UD should be minus UI, so it's just minus this region. Okay, so you do that, you impose that, and then from Kirchhoff-Helmholtz, it's also fairly easy to show that UD is identically 0 outside. But what do those source coefficients look like, and how do we get those source coefficients which are evaluated at the point? How do we derive those from an integral over a closed contour? Well, we do it in the following way, again, stemming from the original work, and we say that the active field is essentially the sum, so a finite sum. We break the contour up into specific segments, okay, so it remains the same integral, obviously, but now we break it up into segments. So we've got delta CL from L=1 to L, anticipating that we're going to have L active sources. And of course, what we can do then is re-expand, because if you think about the original form of Kirchhoff-Helmholtz, then essentially it's a distribution of dipoles and monopoles, as everybody will know, with specific amplitudes. But that, of course, is integrated over a closed contour. So instead of integrating them over a closed contour, what we want to do is push all of those, that distribution of dipoles and monopoles onto a single point in space. And of course, what we can do for that is to use the addition theorem for Bessel functions due to graph. Okay, so what we say is that if we sit at this point here, how do we express the function, okay, outside here? How do you express these functions? So we can take our kind of Green's function, and for x minus xl greater than y minus xl, so outside this disk here, we can express the Green's function in terms of this modal sum over sort of incoming and outgoing fundamental solutions. We can put that summation back into the integral, and then of course we can actually evaluate those integrals if we can. And the key point here is that, of course, it's no good having this contour here, because that's within the region in which our expansion doesn't work. So we need this contour to be pushed out onto the boundary of this disk. So we deform this bounded disk, and that's essentially what tells us the shape of our silent region. Okay, so we do that, we push it out into this, and then this is where this kind of union of disks come from, because we can choose our active source to sit anywhere here. Okay, it could sit here or here or here. It just means we're going to get a slightly different boundary of that active source region. Okay, and of course, some are better choices than others, and that's where the idea of the Platonic solids comes from. So in order to get an explicit formulation for the active source coefficients, then what we do is expand the incident field into this sort of standard form in terms of our incoming fundamental solutions. And again, write everything down in the right form on this contour. This summation here just involves known constants. So of course, Q is known from the form of the incident field. That's dependent on K, the wave vector. And then these S hats are essentially just constants. Okay, so it's fairly straightforward to just do that expansion if you have Paul Martin's book on Bessel functions and multiple scattering theory. So I'll implement that, and you can go through and you can show that a very nice way to do it, if you have a Platonic distribution or this kind of regularity, is you have this kind of interlacing sets of disks, and the face delta C is bounded by this set of circular arcs that are sort of sitting inside these spheres. Okay, so this is a cross section through the three-dimensional space, and of course, as you move through, you see a slightly different region C, which is dictated by these regions here. Okay, so the key point is that if you choose this active field properly, then it nullifies the nullifies the scattered field inside the quiet zone, whereas it's 0 outside. Okay, so 5 Platonic solids, you have these 5 different configurations, and in particular, so the region inside here, the sort of orange region is the silent region. So we've got 5 different cases, and if you distribute the active sources in this way and you calculate the active source coefficients properly, that's what the active source quiet zone should look like. Okay, so how do you actually determine what these active source coefficients are? So what you could do if you want to do is just go through and blitz through those integrals. In particular, you could distribute those active sources anywhere in space, but what we've done here is to choose those Platonic distributions of the sources in order to make things a little bit more straightforward from a computational perspective. So we'll just run through now why indeed we did that. So if we write down the active source coefficients, then they have this sort of quite nice form, because A is just a constant that's fixed for a given L. K is the wave vector, and of course XL are the locations of the active sources, and delta CL are the these surfaces that sit on the boundary of the quiet zone. So we have to carry out these integrations. Okay, it turns out that the active source distribution is nicely split, really, in terms of a set of coefficients that are dependent on the incoming wave vector properties, and a set of coefficients that are only dependent on the geometry of the source distribution. Okay, and it's this sort of splitting of this form that allows us to compute things quite efficiently. So these integrals pop up, okay, these integrals in the summation, and it is these integrals in 2 dimensions that we can determine explicitly. We're not as fortunate in 3 dimensions. Thus far, we haven't deduced a sort of analytical form for these integrals, and so we have to determine an efficient computational way of doing those integrals for a given parameterization G of phi of this surface. Okay, so Chukya managed to formulate this in a very nice way involving the incomplete beta function. So because that's evaluated nicely in Mathematica, MATLAB, etc., then it's quite a nice way to evaluate these integrals. And regardless of the fact that you have significant summations here, then that turns out to be a fairly efficient way of doing things. So, okay, so let's say that we've evaluated one of these integrals. Okay, so say we've got L equals 20, we've got the largest number of sources for the Platonic solid that we're interested in. then of course, in principle, that gives us 20 such integrals to evaluate. And that's really where the time's taken on computation. So it's better if we can try to reduce that amount of time to be more efficient, especially if we want to evaluate these source distributions quickly. So we can get around that by exploiting the properties of Platonic solids, okay, and exploiting the form of this source distribution, the fact that you've got this wave vector decoupled from this term involving the geometry. So really the geometry is kind of irrelevant, okay, because if you do an integral over this surface here, then it doesn't really matter that it's transformed or rotated around the Platonic solid. And the only thing that really changes is this term involving the wave vector. Okay, so we'll exploit the fact that the source distribution is uniform and you have this rotational symmetry associated with the Platonic solids. We label the bottommost active source as you know, this one x1 that's located at minus x0 on the z-axis. And it turns out that we can essentially determine all of the other active sources just via some post-processing involving a rotation matrix associated with the single set of active source amplitudes associated with this active source at the base. So essentially, we only have to determine one set of active source amplitudes in order to determine all of them. Okay, and how do we do that? Well, we define this kind of rotated space, so x prime, so to speak, such that you rotate from the original coordinate space to the rotated coordinate space via this rotation matrix, okay? Now, of course, delta C prime is the same as delta C because it's the same shape. We've got a Platonic solid. Okay, we know the properties of this rotation matrix. And because the geometry dependent part of Q, L, and M is rotationally invariant under this rotation, then we can essentially just determine this straight away because we already know Q1. And then the only other thing that we need to know is the incident field part of that sum. And that just changes to K prime, of course. And then what we do is just equate the two different descriptions of the active field. So we have the active field evaluated at x and the active field evaluated at x prime. We know that Q, L, and Q1 are the same by this K prime notation. And of course, then we just use the transformation between the different spherical harmonics in the coordinate systems, again, via a kind of Graph's addition theorem. And you go through the analysis, and essentially it tells you that you can determine all of the QLs via this, essentially this matrix operation on Q1. Okay, so you determine Q1, you know the set of source amplitudes required from the active source amplitudes at the base. And as soon as you know those, and the set of rotation matrices associated with your Platonic solid, you can determine all of the active source coefficients. But in order to create this kind of silent zone, you go through the analysis, you've got your incident field for L equals 20, for example. This is the active field that's required for L equals 20. This is a cross section, of course, at Z equals 0. And you go through, you add those together, and you find exactly what you should do. Okay, so you get identically 0 in the middle here, and you end up with a nice incident plane wave outside the active source region. So of course, what we really want to do is show that this works when you've got an elephant in there, or a sphere as we normally take. So for the case of Ka equals pi, so A here is the size of the sphere, so it's a fairly high-ish frequency, I guess. And N equals 10, so N here is the number of multipoles. That's a fairly high multipole number, but you kind of need that when you get to frequencies as high as this. And you see the active source kicking in and working pretty well. So this is obviously without any active sources, and this is then with. Of course, things work well. And so Chutkin did a great job of coding all that up because, as you can imagine, that's not an easy job. So of course, the sort of thing that you'll be interested in is, does this work over various multipoles? Does it work over the various different types of Platonic solids, or how does it work? And the dependence on the frequency. So if we think about Ka ranging from 0 to pi, so kind of from low to mid-ish frequencies, I guess, and we define the kind of scattered power normalized on the case where the active field is 0. And essentially, so we plot the sort of log of this, and as soon as this becomes negative, that means that we've reduced the amount of scattering, of course. So that's really what we want to achieve. So even with L equals 4, in the case of N equals 10, so a fairly high-ish multipole count, then even the L equals 4 case does pretty well. And of course, you see this kind of dropping of the scattered power as you increase the sort of Platonic distribution, as you may expect. You get this kind of nice interaction between the L equals 12 and 20 case, and that's pretty interesting. I think that probably is to do with the fact that the quiet zone is quite a bit larger for the L equals 12 case than the 20, just associated with the sort of geometry of the Platonic solids. Of course, what we may be interested in is what can we do with N equals 1? Okay, so in a practical setting, you might only be able to achieve monopoles and dipoles. So can you actually do anything practically there? So N equals 1, you can see that, well, you can reduce scattering. So even for the L equals 4 case, you actually achieve a pretty good reduction in the amount of scattering. But certainly for the L equals 12 and 20 case, then you certainly achieve a significant reduction in the scattering. But what's particularly interesting here, anyway, interesting to me, is that this graph really illustrates that blindly increasing L and the order of multipoles is not an optimal way of going. Okay, so if you fix the monopole and dipole and then optimize those source coefficients, that's a very different problem to what we've done here, where we fix the source coefficients in order to create a quiet zone and then truncate that multipole. Okay, so the kind of problem that you're interested in it dictates on kind of how you approach these active source problems. And then finally, a fairly interesting thing to plot is how many multipoles do you need in order to reduce scattering by 10 dBs, for example, which is a pretty significant amount. So obviously when L equals 4, you need a much greater number of multipoles than when L equals 20, for example. So when L equals 20, you can actually get away with a fairly lowish number of multipoles, even for sort of fairly high frequencies. So conclusions from sort of this part of the talk, I guess. Firstly, that we can actually use active exterior cloaking in 3 dimensions for a variety of different configurations of the active source distribution. The Platonic solids seem to be a particularly nice way of doing it, because you get that nice rotational symmetry that allows you to implement the methodology very efficiently. And these kind of quasi-explicits, it's not explicit because we have to do computations, but the quasi-explicit expressions turn out to be fairly efficient to evaluate. You only need to evaluate one set of source amplitudes to fully determine all the other sets of source amplitudes, which is fairly neat. And in some cases, in the low frequency, then the monopole and dipole sources seem to be quite effective. So one step that you could take further to this is you could distribute sources in a slightly different way, so that you had sort of 2 types of surface integrals. Okay, so the nice thing here was that every single surface integral looked the same, pretty much, bar the kind of wave vector. But if you wanted to, you could distribute sources in a way that you had all different types of symmetries. So you might be able to have 2 families of surface integrals, and then you have those 2 types of surface integrals to evaluate. So you could extend this in any number of ways you'd like to. So this work is about to be submitted, and again, Chuck Kim's done a great job of writing that paper. So where are we? We're about 27 minutes, so that's pretty good in terms of what I want to say. This part of the talk is only fairly short, and it's some work that I've been doing with Phil Cottrell, who's a research fellow at Manchester, and David Negro, who works for Thales UK. And really it stems back to some low frequency resonance work that we were trying to do associated with the giant monopole resonance. So some people know about this, some people don't. It depends on how much elasticity you've done. But essentially, if you have a traction-free void in an elastic material, and if mu is much less than lambda, then you have something called a giant monopole resonance, which is exactly what it sounds like. It's a resonance in the monopole part of the scattered field, and it stems from the kind of softness of the material, essentially. Okay, so what we do the kind of classical thing that you would do in elastodynamics. You've got an incident compressional wave vector kp. incident at an angle theta p, as it's in the plane, it's planar elastodynamics, and traction-free void radius a. You formulate everything in terms of the normal compressional and shear wave potential, so phi and psi, and this is your traction-free condition on r equals a. You do pretty much, a similar kind of thing to what we were just talking about in the context of active cloaking, but now you're thinking about the scattered field in terms of the standard outgoing fields. So Bn and Dn are the two sets of source coefficients, sorry, scattered field coefficients. And we're going to assume only a compressional incident field. Okay, so you have this kind of standard way of doing things in terms of the T matrix, and the T matrix brings in everything about the properties of the void. So if you wanted to, you could have an elliptical void if you really wanted to do that, and you'd only have to modify the T matrix for a given set of incident wave coefficients. And so what's interesting to us is to look at the scattered energy, so to speak, or this scattering cross section. And there's a nice way of writing the scattering cross section in terms of a sum over the T11 elements of the T matrix. Okay, and so this is quite a nice way to do things, because again, you only have to know the T matrix in order to then deduce the scattering cross section. And we're interested in this case, okay, this case where you get the giant monopole resonance. So we define this parameter psi, which is mu over lambda plus 2 mu. Okay, so for things like rubber or any number of polymers, soft polymers, or incompressible materials, then psi is very, very small. What that means, of course, is that your compressional wave is very long, your shear wave is very short, and you kind of exploit that in order to get this kind of resonance that crops up. Okay, so hopefully you can see this. It's a little bit small, but what we've plotted here, just to give you an indication if you haven't seen it before, is the sort of magnitude of this giant monopole resonance, which is pretty impressive. When you first see these, you're pretty shocked about how large the resonance is. So this is kind of fairly realistic, or somewhere sitting between here and here. So psi is 0.01, so it's a kind of rubbery material. And you see that lambda p over a, so the wavelength over the void radius, is 78.5 here at this resonance. So KSA is order 1, okay, because obviously your shear wave is still of the same order as the void, but the compressional wave is very long now. And you see in particular, if you look at the scattered energy, so scattering cross section, if you go down to psi is 0.001, you have a huge resonance here at very, very low frequency. What's also noticeable here is that there's different ways of defining resonance, right? And so what we've plotted here are the magnitudes of the displacements. So that's the radial and the azimuthal displacements on the surface of the void for the different modes. So m equals 0 is the monopole, of course, and you see here why it's a giant monopole resonance, okay? Because essentially the dominant contribution to the field is the monopole. Pretty much everything else is second, third, or even fourth order, so to speak. But the way that we define the resonance here could be the maximum displacement on the surface, okay? And you get a specific value for lambda p over a. If you define the maximum scattering cross section, you get a slightly different value for the resonance. Okay, so it kind of depends on how you take that, but they're of the same order of magnitude. So what we're going to talk about here is what happens when you start to have interacting voids. So can you use voids in close proximity to manipulate the resonance and to manipulate the far field? And of course, when you have that, there isn't really a sensible way to define the resonance in terms of displacements on the surface of voids, because you've got two different voids. So for us, it seems more natural to define the resonance in terms of the size, the magnitude of the scattering cross section at a given KSA or KPA. Okay, you usually plot in terms of KSA, because otherwise, if you plot in terms of KPA, things become extremely scrunched up due to scale. Okay, so as I say, we're interested in this problem. So you formulate the multiple scattering problem for n voids. Okay, how is this scattered energy modified by the coupling between scatterers? How does the field vary with incident angle, of course, and how does that coupling affect the low frequency resonance? So the interesting thing is that the dominant contribution to scattering, and what we mean by scattering generally is the kind of far field, because that's what you really see, is the monopole contribution. But of course, in reality, what's happening at the surface is that you're getting, and in the near field, is that you're getting various contributions to that scattered field that kind of die away very quickly as you go to the far field. So having these in close proximity means that you can actually exploit that coupling in a way that means that the resonance and the far field is actually modified. So the kind of obvious one to start with is what we think of this as a Covoid Metacluster. So you have two circular voids, both of radius a, again just for simplicity, and they're separated by a distance d. So what happens to the resonance? So what we do here is we plot heat maps of gamma, this the scattered energy. So we plot that for various angles of incidence, and we plot KSA against d over a. So remember, d is the distance between the voids and a is the radius of the void. So as d over a tends to infinity, you'd expect to get the isolated giant monopole resonance. And as d over a tends to 2, that's the smallest value here, that's when these two voids come up and touch. Okay. So indeed, what happens is d over a tends to infinity, you recover the kind of classical isolated void resonance. But what happens in between is very interesting. You get these kind of resonant regions. So the line here is the maximum of the scattering cross section. So you can kind of see these ridges where you obtain the maximum of the scattered power. But of course here, this is when these things are very far apart. And that's essentially that's driven by the interaction between the two voids and the compressional wave. And of course, if we're wanting to think of these as metaclusters or meta-atoms or whatever you want to call them, then we kind of need them to be fairly close together, so we can think of them as almost like a modified inclusion. And so the interesting thing for me anyway was to think about what happens when d over a tends to 2. So when these things come close together, how do they behave and how does that modify the resonance? Well, the interesting thing is that when they touch or close to touching, anyway, we never quite take them to touch because obviously the fact that they touch causes you problems in the computations, but KSA is close to 0.5. Okay, so that's a reduction of the resonance, and in particular, the KPA now becomes 0.05, or lambda p over a goes to 125.7. So the point is you're lowering the resonance by having two voids close together rather than a single void. But more than that is the following: the fact that if you take a covoid, okay, so two voids fairly close together, d tends to 2a, then the covoid area is equivalent to a circle of radius root 2a. Okay, so the GMR frequency of that sort of equivalent area void would be kPa hat 0.084. If you write that in terms of a, the original radius that we're interested in, that gives you a lambda p over a as about 100, 106, 107. The close to touching covoid GMR gives you a lambda p over a is 125.7. So what that's telling you is that for a smaller area, you're actually achieving a lower resonance. So a smaller area covoid gives you a lower frequency resonance than an equivalent area single void. Okay. So that essentially is due to that local interaction, that scattering that's occurring between the voids in the near field. Coupling gives you this kind of lower resonance. And now the extra thing that you might be interested in, because if you're thinking about doing this in a sort of multiple scattering computational way, you might not really want to do, computations where you're doing this explicitly. So the question is, can you approximate this via some sort of monopole field? Because, for a certain distance away, this will just look like a monopole. So close in, that coupling gives you this interaction between the voids, whereas far out, you're just seeing a monopole pretty much. And so you can see what happens here. So these are two different plots. Let's just focus on this top one here. So a certain value of this is psi, the rigidity, apologies. Psi is 0.01. That's a pretty realistic case. And so I can't remember which way around this is now, but the red field is the exact field. And you have two different monopole approximations here. So for the first monopole approximation, which is the simplest possible monopole approximation, is just to approximate each of these scatterers individually with a monopole. Okay, and then you just literally just take that monopole field. And that gives you this kind of blue dashed curve, which, although it's pretty bad, it's actually, sorry, it's pretty off the exact field. It's pretty good, actually, in the vast range of d over a. So the point is that if you wanted to approximate the field, then the monopole approximation is actually reasonable for d over a, away from 3, for example. But what gives you that kind of nice coupling is that local interaction. And so the additional monopole approximation here is what happens when you take into account the interaction locally, okay? But then once you've done that multiple scattering and you've seen, you know, that the dipole coefficient from here scatters into some monopole field from this one, then you then solve the full multiple scattering problem, but then you just retain the monopole field. And it turns out that that's an extremely good approximation to the full field. So that is one way that you could approach things if you wanted to do things approximately. And then, of course, you know, you can do all sorts of things, but for the trivoid metacluster, as we call it, there's kind of 3 different configurations. I suppose this could be a quad because there's one in the middle here, but the sort of planar line, what's interesting is that because you're in a fairly compact region here, then this is the angle of incidence here. So for 0, 30, 60, and 90, there's very little difference in the actual resonance here. Okay, so the cross section itself is sort of maximum at the same KSA, but the actual amplitude itself varies. Okay, and the difference between this and the actual triangle, so that we call this the triangle resonator, you know, you get a much lower frequency resonance associated with these this line of voids, and that's probably partly to do with this middle one being more constrained essentially than this case, where there's a kind of symmetry to the constraints. You see this additional resonance sort of that's kicking in here, and that's almost certainly associated with, you know, this kind of Wood anomaly effect that kicks in. It's a fairly weak effect at the moment, but if you made that into a sort of, you know, line array, proper line array, then you have this additional resonance that kicks in. But the key point is that the GMR of the line array trivoid is now KSA is 0.4. So you're going from, where were we, 0.5, I think it was, 0.5 with the 2 void case to 0.4 with the trivoid. And what successively happens is that the resonance gets lower frequency, but of course the resonant amplitude per void, so to speak, is lower. So, you know, what you sort of get with one, it takes away with another. But in terms of tuning the properties, or the resonant properties, or the frequency dependent properties of your metamaterial, for me, this is a fairly interesting effect, so to speak. And you see with this kind of, you know, triangle plus 1 in the middle, you get this kind of, you know, resonance that sits between these, but that is increased in amplitude purely by the fact that you've got more area. So the more area you have, you will always get a larger resonance. Okay, so takeaways from that. Kind of local coupling allows you to modify the GMR response. You know, this is kind of the early stages. I think you could do something fairly interesting with this in terms of overall properties. The low frequency resonance can be made lower with the same fixed area of voids. You know, so if you only want a certain density of material, then, you know, you may be more interested in drilling 2 holes than 1, for example, if you want a certain scattering effect. The void configuration allows you to tune the resonance, of course. So, you know, you can have any number of different types of these scatterers in the material. Monopole approximations can be useful. Okay, so that's important, certainly in terms of applications and you know, fast computations. And in the compact regime, you can think of these kind of equivalent single scatterers. So this is where these monopole approximations might be useful, because if you are in a compact regime, it might be much more computationally efficient to just think of an equivalent scatterer rather than, you know, this whole array of meta clusters. So, you know, you characterize the meta cluster, and then you impart the properties of that meta cluster to a kind of single effective scatterer in terms of computations. And of course, you know, you could combine with other kind of elastic resonators. We've all seen the humongous work that's done on that in recent years. So this work's going to be submitted to this special issue of Proceedings on asymptotic methods for metamaterials. And now for some shameless advertising just to finish off. So you heard me mention wave motion earlier. So this is a journal that's sort of dear to my heart. And for many of you, this impact factor is ridiculously low, and I apologize for that. But, you know, it's a serious journal, and we try to do We tried to do things properly. We've tried to increase the kind of speed to review over the last couple of years. So we're also considering at the moment ways to bring about some kind of letter format to the journal. So, you know, whatever you're thinking about, if you could just take a look at wave motion and think about whether it may be suitable for some of your work or some of your colleagues, I'd appreciate that. And finally, if we're able to do any traveling by then, Phononics 2023 will be in Manchester. 2021 was of course postponed. It was meant to be in Marrakesh. Unfortunately, that was postponed, and we're hoping that will happen next year. But we're hoping this will happen in Manchester, and we can treat you to some lovely Manchester weather, and whatever we're going to do, whether it's a trip to Old Trafford or to the Man City Stadium, if you prefer Man City, or going to the Peak District, the Lake District, North Wales, you know, the Cheshire Plains. We'll have lots of fantastic activities for you to come and enjoy. Okay, so just some acknowledgements to close. So Chuck Kim, thanks for doing such a fantastic job with the active cloaking work, and Tom, of course, heavily involved with that project, and Phil and David for all their work on the GMR stuff. And of course, I need to thank EPSRC for funding, and University of Manchester, who provided a Dean's Fellowship for Chuck Kim. So thanks again to Bogdan for organising, and happy to answer any questions.
Thank you very much, Will, for this fantastic talk. So we welcome any questions from the audience. So